Welcome to lecture 18. In the previous lecture I have explained a global calculation of the zeroth equivariant homotopy groups of the symmetric product spectrum. So let me remind you of the notation. SPN is an orthogonal spectrum that is made up from the nth symmetric products of all the representation spheres, these varying through all inner product spaces. And we're interested in the equivariant zeroth stable homotopy groups of this orthogonal spectrum, but we will describe it in a global fashion. In the global description, it's actually a cyclic global functor, so it's a quotient of the global Burnside ring functor by a single relation. And for this I have to recall this element Tn, which can be described in two essentially equivalent ways. If you want to describe it as an element in the Burnside ring of the nth symmetric group, so I have to give you a virtual finite sigma n set, and then it's n times the sigma n set with just one point, and I subtract the tautological sigma n set with n points. In terms of the sigma n equivariant zeroth stable stem, this would be n times the multiplicative unit minus the transfer from sigma n minus 1 to sigma n applied to the unit in the equivariant homotopy ring of the symmetric group 1 lower. What I explained last time is that the inclusion of the sphere spectrum as the first symmetric product into the nth symmetric product descends to an isomorphism of global functors from the Burnside ring global functor modulo the global subfunctor generated by this single element onto the zeroth homotopy group global functor of SPN. Today I want to make this global calculation more concrete by plugging in a specific compact Lie group in this side and hence determine the G-equivariant zeroth stable homotopy group of SPN on the other side. I will also pass to the limiting case, so this was for n greater or equal to 0 a finite number, but we'll get a similar result when n is infinity. And I also want to explain a theorem of Marcus Hausmann that determines the rationalized higher equivariant homotopy groups of the symmetric product spectra, at least for finite groups. Before I get into things, I would like to remind you of something that we discussed in lecture 9. So there I gave a similarly looking formula. There I talked about a global tone spectrum, little m capital O, and we determined the homotopy group global functor in dimension 0, and this was something of a very similar flavor. So I showed there this was isomorphic to the quotient of the Burnside ring global functor generated by a single relation. This was the transfer from the trivial group up to the cyclic group with two elements, and of course in the present notation we could also say this is the transfer from the trivial group to sigma 2. So for n equals 2, the second symmetric product, we have a similar kind of relation here. In both cases, the transfer from the trivial group to the second symmetric group is set equal to something else, but there's a difference. Here, the transfer was set equal to 0, whereas here we're going to set the transfer equal to 2. And of course, this influences the answers. Like here, we figured out concretely what this is at one compact Lie group. It's an F2 vector space. And the basis is given by the transfers from all subgroups H to G, such that H has a finite Weyl group of odd order. So here we're not going to get F2 vector spaces, we're going to get abelian groups that will often be free and sometimes they will have torsion. Let me introduce a piece of notation, so let me abbreviate this Burnside, this global subfunctor of the Burnside ring functor generated by Tn as In. So this is sitting inside the Burnside ring global functor, and now let me explain certain elements that will play an important role when we specialize to one group at a time. So for k less than equal to h, nested closed subgroups of the compact Lie group G, and I'm going to assume that these have finite index one each other. So the index of h in k is finite. So in other words, these have the same dimension. They can have a strictly smaller dimension than the ambient group, but they have to have the same dimension. And then we define an element that I call T sub k upper h, and it's a generalization of this element Tn. I'm going to take the index of k in h times the transfer from h to g of 1, and I subtract the transfer from k to g of 1, and this lies in the Burnside ring of G. So at the present point, there's no assumption about finite Weil groups. This is something I can certainly always write down. We will only be interested later, because only then do we get non-trivial elements, when at least H has a finite Weil group in G. It will certainly be possible that H has a finite Weil group, but K has an infinite Weil group. Then it's still a valid definition, just that this second summand might be 0 sometimes, depending on the Weil group conditions. So here, this is made so that it lies in the augmentation ideal, because the difference between k and h is the index, and here I'm exactly multiplying by the index, so this difference will lie in the augmentation ideal of the Burnside ring. And we've already seen an example of this. The class T sigma n minus 1, sigma n is just a different name for the class Tn up there. So these classes are generalizations of the other ones. Now here is the main proposition, which makes this result concrete, and it goes as follows. So let G be a compact Lie group, and n greater or equal to 2. Then the abelian group In of G, so the value of this global functor at the given group G is generated by the elements TKH for all G conjugacy classes of pairs K in H, so these are closed subgroups and they sit inside each other, such that first of all the index is not only finite, but the index is less than or equal to n. That is this n that we're presently considering, the n of the symmetric product, and moreover we want that the Weil group of H and G is finite. I mean, otherwise it would still be true, but we would just talk about the 0 elements. We don't need them. The proof of the proposition depends crucially on the fact that we have this explicit understanding of what global functors are, or equivalently that we have this presentation of the global Burnside category in terms of transfers and restrictions. The global functor In is by definition is the image of the morphism of global functors from the represented global functor, represented by sigma n, to the Burnside ring global functor that's classified by the class Tn. Classified by the element in Tn. Now we're going to substitute this compact Lie group G here and here. So In of G is the image of the map from a sigma n G to A of G. And this, we calculated, it's a free abelian group generated by classes of the form transfer from H to G composed with alpha upper star. And then I'm not going to repeat the conditions, I think you know them by heart right now. Alpha is some continuous homomorphism defined on H, and H has the finite Weil group in G. So this map will send one of these generators to transfer from H to G of alpha upper star of the class Tn. So we have to work out what kind of classes we get from such expressions. So let us factor alpha, which is a continuous homomorphism from H to sigma n, through its image. So I'm going to factor this as a surjection that I call beta onto a group gamma that is just a subgroup of sigma n, that's the image. And then this is the same as transfer from H to G, followed by beta upper star applied to the restriction from sigma n to gamma of the element Tn. So the reason I've broken alpha up this way is that now we have to move the transfer past the other operations, and this will be different depending on beta upper star, that's an inflation, and here we'll use the double coset formula. So let's first calculate this term in here. So what is the restriction from sigma n to gamma of the class Tn? So this has two terms, so this was n times 1, and that restricts to n times 1, and then minus the restriction from sigma n to gamma of the transfer from sigma n minus 1 to sigma n of 1. So now we have to use the double coset formula to rewrite this term. So this is n times 1 minus the sum, and this is a simple case of the double coset formula because these are all finite groups that show up here, so there's no analysis of orbit type stratifications necessary, so it's just a sum over double coset representatives in gamma mod sigma n minus 1. And then we have the transfer from gamma intersected with the sigma conjugate of sigma n minus 1 to gamma of 1. Now in the general double coset formula there will also be a restriction and a conjugation, but if you apply restriction and conjugation to 1 you just get 1 again. And this is nothing but the sum of sigma in double cosets, gamma mod sigma n minus 1, and then the class of gamma and gamma intersected with the sigma conjugate of n minus 1. So from here to here I've broken the n times 1 apart and moved it up in here, so this equation uses the fact that n, which is the index of sigma n minus 1 in sigma n, is the same as the sum over all the coset representatives of the relative indices of all sigma in gamma mod sigma n minus 1, and then the index of gamma intersected the conjugate in gamma with gamma. Okay. Now we will apply beta upper star to this. That's an inflation, that's easier to compute, but I need more space on another whiteboard. Applying beta upper star to the relation we have just deduced, we get the following. Beta upper star of the restriction from sigma n to gamma of Tn is the sum over double coset representatives, gamma sigma n modulo sigma n minus 1, and then beta upper star of T gamma intersected the sigma conjugate of sigma n minus 1 all the way to gamma. And now beta is a surjective homomorphism and transfers commute with inflation, and that means that here we just have to pull back under beta everything. So this is going to be the sum again over double coset representatives, sigma n mod sigma n minus 1, and now we have T, H, and beta inverse of gamma intersected the conjugate of sigma n minus 1. Now I will apply the transfer from H to G. So transfer from H to G of beta upper star of the restriction from sigma n to gamma of Tn. And because beta composed with inclusion is alpha, this is the same as the transfer H to G of alpha upper star of Tn. Transfer is additive, so I get sum again over double coset representatives. And then the transfer from H to G of T beta inverse of gamma intersected the sigma conjugate of n minus 1 up to h. And now this is the same as, again, sum over double coset representatives, and then just t from beta inverse gamma intersected gamma sigma n minus 1 to h. So this might look a little bit weird, but it's just a special case of the relation transfer from h to g of tk to the h is tkh. So this might look weird because it seems like I'm doing something to an element and getting the same element, but this is because our notation is being abused. This tkh is formed relative to h as the ambient group, whereas this is formed relative to g as the ambient group. And if I take this element and change the ambient group from h to g, I get the element with the same name, which nevertheless is a different element. So this is what I get out. And now I observe that because sigma n minus 1 has index n in sigma n, and moreover, if I take gamma modulo gamma intersected sigma n minus 1, so this injects into sigma n modulo the conjugate by sigma of gamma n minus 1. This has n elements. Because this injects, this has less than n elements, and the index of this group in this is exactly the index of this group in this. So the index of h, or beta inverse of gamma intersected of gamma sigma n minus 1, the index of beta inverse of gamma intersected with the conjugate of sigma n minus 1 in h, we deduce that this is less than or equal to n. So in other words, this element is a sum of things which are exactly of the form tkh with the index less than or equal to n. So this shows one of the two containments, because the image of the map is ing is generated by these classes here, and every such class is a sum of classes that we claim generate the image. So this is one of the two inclusions. The other inclusion amounts to showing that the elements tkh, subject to those conditions, are actually contained in In of G. So now we consider a pair as above. Let k less than or equal to h be as in the statement. So in particular, the index of k and h is less than or equal to n. So we choose a bijection of sets between the set h mod k and the set with m elements, and then m will be less than or equal to n. That is this index assumption down here. So h acts by left translation on this, and this choice of bijection turns this into a homomorphism. For this we get a homomorphism alpha beta from h to sigma m, such that h modulo k becomes H-equivariantly isomorphic to beta upper star of 1 up to m. So the tautological sigma m set with the elements 1 up to m, and then acted upon by h by conjugating with this bijection. And we have the element Tm, which by design lives in Im of sigma m, and this is contained in In of sigma m. That's because m is less than or equal to n, and because a larger t restricted to a smaller symmetric group gives the smaller group, so these global subfunctors form a nested sequence. And because this is a global functor, we now get that tkh, which was the transfer from h to g of hk times 1 minus transfer from k to h of 1. So this is not quite the definition of tkh, but if you combine the definition, this, and use the transitivity of transfers, you get the definition. So this is the transfer from h to g applied to beta upper star of the element Tm, that is this isomorphism of h sets, and this is contained in n of G, because first of all, this is contained in M of G, and as a global subfunctor, it's closed under restrictions and transfers. So this shows the other relation, and hence it completes the proof of this proposition. Let me draw one immediate corollary of this. So if G is finite, let G be finite of order n, and then we conclude that In of G is the entire augmentation ideal, because if G has order n, all the indices of nested pairs of subgroups have to be divisors of n. In particular, they have to be less than or equal to n, and this implies that from there on, at the particular group G, this sequence of global subfunctors has to be constant because it already reaches everything, and the consequence of this is that pi 0 G-equivariant of Sm is isomorphic to the Burnside ring G modulo I of G. We would have Im, m is greater or equal to n. We would have Im of G here, but that is everything, and this is isomorphic to Z. So an immediate consequence is that for a fixed finite group, the sequence of pi 0 G equivariant stabilizes, and it stabilizes at the end stage where n is the order of G, and then we have already reached the limit group, which is just Z. So for every fixed group, the system stabilizes, but of course it does not stabilize uniformly, because the point where it stabilizes depends on the order of G. And we will soon see another example that shows that there's no global bound from which point on for all finite groups the sequence stabilizes. Here's another infinite family of examples. So let P be a P group, P some prime, and then I claim that we can completely identify what this sequence of global subfunctors looks like. I claim that the value of An at P is either 0 for n less than P, or it's the full augmentation ideal when n is greater or equal to P. The first case is clear because since this is a P group, all the relative indices of proper inclusions K and H always have to be powers of P. In particular, they can never be smaller than P. So for n less than P, there are simply no generators of In of G. That's why it's 0. So the thing that we really need to show is that for n greater or equal to P, you have everything, or once you get to P, you have everything. And this depends on another property. Here's an auxiliary claim. For every subgroup H of P, of this P group, there is a sequence of intermediate groups, of subgroups, starting with the given H, contained in H1, and so on, contained in HK, which is everything, such that the relative index is always exactly P. So such that the index of Hi in Hi plus 1 is P and not some proper power of P. So let me prove this subclaim in two cases. So every P group has a non-trivial center. That's an elementary fact from finite group theory that I need to use. So there's a non-trivial center, and in this center there's a central subgroup with exactly P elements. So let C be a central subgroup of P with exactly P elements. And then I'm going to distinguish two cases. So case 1 is when C is contained in H. And then we do an induction on the order of P, and we apply the claim inductively to H modulo C, which is a subgroup in P modulo C. So this has smaller order. So here we can find an intermediate sequence of subgroups where the relative index is exactly P. And then we take pre-images under the projection. And take pre-images under the projection from P to P mod C. So this is then the sequence that does the job. And case 2 is when C is not contained in H. And then we apply case 1, apply 1 to the group generated by C and H, because C has exactly P elements, and it is not contained in H. This is exactly P times as large as H is. So the order of this group is the order of H times P. So here, case 1 applies, so we have some intermediate sequence of subgroups H, K equal everything, and H lies in here, and this relative index is exactly P. So that gives us this sequence in the second case. So this was the proof of the subclaim, and now we make a calculation. Now I look at the element T, H, P, and I expand the definition. The definition was that this is P to the K, where this is the order of the index of P in H. So index of P in H is P to the K, minus the transfer from H to P of 1. I'm rewriting this as the sum I equals 1 to K, and then P to the I minus 1 times T H I minus 1 Hi. So when I expand this sum, then exactly two adjacent terms will cancel out because the relative index is exactly P, and then the two extreme terms will be these two things. So this shows that this is contained in I P of P, because this is an element of a relative index exactly P. On the other hand, the augmentation ideal is generated by all these classes. By the classes T, H, P for all subgroups H and P. So it must be everything. So I P of P must be the full augmentation ideal because it contains generators for the augmentation ideal. So this completes the claim up there, and so we can, in particular for P groups, determine the zeroth P equivariant homotopy groups of the symmetric products, and we get two cases. We get the full Burnside ring for n less than P, because in this situation we're not dividing out by anything, and we just get Z for n greater equals to P, because in that situation we're dividing out the full augmentation ideal. So for P groups, the sequence is just constant the Burnside ring functor, and then it's constant Z. In particular, because primes can be chosen as large as possible, this shows that there is no universal bound on when this sequence of zeroth equivariant homotopy groups stabilizes for finite groups. For a fixed finite group it stabilizes, but there's no bound at which it stabilizes for all finite groups together. The next examples are some symmetric groups for small numbers. The first one we've already taken care of. The symmetric group on two letters happens to be a two group, so the previous example takes care of this. So we've already seen that the second stage of the filtration is everything. And we've seen that pi 0 sigma 2 equivariant of SPn is Z for all n greater equal to 2. So for the first symmetric power, which is the sphere spectrum, you have the Burnside ring of sigma 2, which is 3 billion of rank 2, and already at the next step you just have a single copy of Z, and then from there on everywhere. So let's look at the next larger example, the symmetric group on 3 letters, which is also the smallest finite group that is not a P group for some prime P. So here's the subgroup structure. There's the big group sigma 3, which is 6 elements. Then we have the group with 3 elements, which could be called the alternating group, or it's also a cyclic group with 3 elements. Then we have the subgroups of order 2 generated by any of the 3 transpositions, and we have the trivial subgroup. So this diagram records the conjugacy classes of subgroups, their relative containments, and you can get at the indices because I've written the orders on the side. These 3 groups are normal, this one's not normal, so there's 3 in this conjugacy class. Because there are 4 conjugacy classes of subgroups, the Burnside ring has rank 4. There's 3 of rank 4. So the augmentation ideal is free of rank 3. And it's freely generated by 3 classes. And a convenient basis would be the element T3, which is transfer from sigma 2 to sigma 3. Then the element that I call P upper star of T2, which is T, sorry, this is not transfer, this is T. This is T from A3 to sigma 3, and then we would also have T from the trivial group to sigma 3, but it's convenient to use instead a different generator, namely the transfer from sigma 2 to sigma 3 of the class T2, and if you expand the definition, this will be 2 times T of sigma 2 sigma 3 minus T of E sigma 3. So this is not the most obvious basis, but because this is one of the basis elements and 2 times this is here, this is also a basis, and I should say what P is. So P is the unique homomorphism from sigma 3 on to sigma 3, the unique surjection. So in this situation, the relative indices are either 2, like in this case, that's relative index 2, that's relative index 2. So already by dividing out the I2 of sigma 3, these will get identified. The remaining 2 classes will not get identified in the second step, but only in the third step. So we get out that I2 of sigma 3 is freely generated by 2 elements. The element that correspond to this index 2 inclusion and to this index 2 inclusion. And this is P upper star of T2, and the transfer from sigma 2 to sigma 3 of T2. And I3 is everything, because then you're also adding these index 3 inclusions, the classes for those, and then you have everything. I3 of sigma 3 is the whole augmentation ideal of sigma 3. And then we can get that pi 0 sigma 3 equivariant of the sphere spectrum, where that's the Burnside ring, A of sigma 3. I already had this here, this is free of rank 4. Pi 0 sigma 3 equivariant of SP2. So there we're dividing out 2 generators. This is free of rank 2. And then pi 0 sigma 3 of SPN is just a single copy of Z for all n greater equal to 3. The last example that I want to discuss in a certain amount of detail is the next symmetric group, sigma 4. This example can serve to illustrate a bunch of features. So first of all, it will show that if you know your finite group or your compact Lie group well enough, so if you know all the conjugacy classes of subgroups and their relative indices, then it's almost a mechanical task to work out these calculations, and you could maybe even write an algorithm to do that. On the other hand, the next example will also show that the explicit answer is not particularly enlightening, and that you maybe don't want to do this explicit calculation, at least if the group is sufficiently complicated. The next example will also illustrate another feature, namely that there can be non-trivial torsion in these G-equivariant zeroth homotopy groups of the symmetric product filtration. So far, we've only seen examples where pi 0 G-equivariant is a free abelian group, and the next example will show that there can be non-trivial torsion. The symmetric group sigma 4 has 11 conjugacy classes of subgroups, and representative subgroups are displayed in this diagram. The left column lists the order of a subgroup, and lines denote subconjugacy. There are 2 conjugacy classes of elements of order 2, the transpositions, denoted here by sigma 2, and the products of 2 disjoint transpositions. The group A3 of order 3 is generated by a 3 cycle, and it is a 3-Sylow subgroup of sigma 4. There are 3 distinct conjugacy classes of subgroups of order 4. the group V4 containing the three products of two disjoint transpositions, the subgroup that leaves the subsets 1, 2 and 3, 4 invariant, and the cyclic subgroup generated by a 4 cycle. The subgroups V4 and sigma 2 times sigma 2 are abstractly isomorphic, but they are not conjugate inside of sigma 4. The group of order 6, denoted by sigma 3, consists of all permutations that fix the element 4. The group of order 8 is a two-pseudo subgroup of sigma 4. It is the normalizer of sigma 2 times sigma 2, and it is abstractly a semi-direct product of sigma 2 acting on Z2 times Z2 by switching the factors. The group of order 12 is the alternating group. Of all these subgroups, only the trivial subgroup, the group V4, and the alternating group are normal in sigma 4. As there are 11 conjugacy classes of subgroups, the augmentation ideal of sigma 4 is free of rank 10, and the Burnside group is free of rank 11. There are a lot of index 2 inclusions, each of which contribute a generator to I2 of sigma 4. Dividing out by I2 of sigma 4 collapses all these contributions from subgroups that are index 2 in a larger group. So the Burnside ring modulo I2 is generated by 3 elements, and it is in fact free of rank 3. The inclusions of index 3 add more generators to I3 of sigma 4. If we add all inclusions of index 2 or 3, the graph becomes connected. This means that rationally, all classes in the Burnside ring modulo I3 are multiples of the multiplicative unit. However, integrally, the class previously denoted T4 is not contained in I3. There is an exceptional relation. This means that the class T4 becomes a class of exact order 3 in the Burnside ring modulo I3. This illustrates that there can be torsion on the zeroth equivariant homotopy groups of symmetric products. As the largest index of two adjacent groups is 4, I4 of sigma 4 is the full augmentation ideal, and the filtration stops at this point. The final answer we get is that the group pi0 sigma 4 equivariant of sp1 is free of rank 11, pi0 sigma 4 of sp2 is free of rank 3, pi0 sigma 4 of sp3 has rank 1 and it has a torsion subgroup with 3 elements, and finally, for n greater or equal to 4, the group pi0 sigma 4 of spn is free of rank 1. In the paper there is one more explicit example that I do in full detail, that is the alternating group A5. In this example you have to go all the way to the 6th symmetric product before the filtration stabilizes. It's also interesting because at some point 3 torsion occurs, at some other point 5 torsion occurs, but it's actually almost painful to go through all those examples and check them in detail. There's also an explanation for why this relation that 3 times the class T4 is already in the 3rd stage of the filtration, why that is an exceptional feature for the alternating group or the symmetric group on 4 letters, which is ultimately connected to the fact that the alternating group A4 is not simple, whereas all the alternating groups from A5 onwards are actually simple groups. Now I'd like to turn to the limiting case. So let me define I infinity as the union for n greater or equal to 1 of these global subfunctors In. This is yet another global subfunctor, so this sequence is an ascending sequence. One is contained in the next, and this is the union. And then the proposition also applies to I infinity, and it shows that I infinity at G, for G any compact Lie group, is generated by the classes T, K, H for conjugacy classes of subgroups K less than equal to H, where K has finite index in H, and the while group in G of H is finite. So again, K and H can have smaller dimension than the ambient group G, but they have to have the same dimension. One has to be of finite index in the other. I want to point out again that this was defined as K index in H times the transfer from H to G minus the transfer from K to G. It is certainly possible that the transfer from H to G is a non-zero element, because we're assuming that the Weyl group of H in G is finite, but nevertheless K could have an infinite Weyl group, so this might well be zero, in which case the element is just this, and it's saying that this transfer is annihilated by multiplication by the index. If the group G is finite, so this was for general compact Lie groups, if G is finite, then of course all subgroups will have relative finite index and finite Weyl groups. So in this situation, I infinity of G will always be the full augmentation ideal. And hence, we will get that for finite groups, pi 0 G-equivariant of SP infinity is isomorphic to the Burnside ring modulo the full augmentation ideal, which is just a single copy of that. And that is, of course, reassuring, because I've told you twice already that SP infinity is globally equivalent to this point set level orthogonal spectrum that I called HZ, which is trying to be an Eilenberg-MacLane spectrum for the constant global functor with value Z, and actually is such an Eilenberg-MacLane spectrum on finite groups. So this is just confirming this fact that I'd already claimed without proof, that SP infinity, or equivalently HZ, on finite groups in dimension 0 is just a single copy of Z. The story gets more interesting if we plug in compact Lie groups of positive dimensions. For dimension G bigger 0, the story is more interesting. And in this situation, we will typically get something that is larger than Z. I want to now give you a decomposition of the Burnside ring and I of G in terms of conjugacy classes of connected subgroups. So let's see here, connected subgroup of G, closed. So if G were finite, this would have to be the trivial group, but now there's more choices. And now I define a subgroup of the Burnside ring. I said A, G, semicolon, C is the freewheeling group generated by transfers from H to G, with the property that, first of all, the Weyl group of H and G is finite. But then also I want to assume that the identity component of H, so that's this H circle, it's the component of the identity in H, that this is this given connected subgroup C. Of course, every subgroup has an identity component, and that's one of the connected subgroups. So every transfer from H to G will be in one of these families where C is the identity component of H. Then this means that the Burnside ring decomposes as the direct sum over round bracket C, which means conjugacy classes of closed subgroups that are connected, and then A of G, C. The reason I'm bringing this up is that these relations will all happen internal to this direct sum decomposition, because if K is less than or equal H of finite index, then they must have the same identity component, and K0 must be equal to H0, and so this class TKH lies entirely in one of these summations. So this lies in A, G, C intersected with the augmentation ideal for C exactly the common identity component. C is H0. So all these relations are homogeneous with respect to this direct sum decomposition by conjugacy classes of connected subgroups, and we get out that also in the limit we get a direct sum decomposition. Pi 0 G-equivariant of SP infinity is the direct sum over conjugacy classes of connected closed subgroups, and then A G semicolon C divided by I G semicolon C, which by definition is this intersection. If G is finite, then there's only one connected subgroup, the trivial group, and this doesn't give us any additional information, so this is interesting for compact Lie groups of positive dimensions. As I'll explain on the next whiteboard, these summands behave quite differently depending on the fact whether C itself, the identity component, has finite or infinite while group. You know, the assumption that the while groups of K and H are finite, in particular the one of H, doesn't necessarily mean that the identity component has to have a finite while group too, and depending on whether that is the case or not, these summands will have different behavior. If the connected group C itself has infinite while group, and we have another closed subgroup whose identity component is this given C, then we can look at the element T, C, H, and this would be index of C in H times the transfer from H to G, and then we would have to subtract the transfer from C to G, but that is 0 because C has an infinite while group, and this element lies in I infinity G C, and that means when we divide out this element that this transfer becomes torsion. So the class transfer from H to G becomes torsion in the quotient A of GC modulo I infinity of GC. And since this holds for all H that have C as their identity component, we conclude that this group A GC modulo I infinity GC is a torsion group. That's what happens if the connected subgroup C has infinite while group. Now in the other case, if C has a finite while group, and we have an H whose identity component is this given C, then we have a sequence of inclusions. So on the one hand we have C, which is the identity component of H. This is certainly contained in H. H is certainly contained in the normalizer in G and H, and this is contained in the normalizer in G and C. Because if something normalizes H, it must also normalize its identity component, which is C, so that gives these containments. Now we have assumed that C in its normalizer has finite index, so we can conclude that also H in its normalizer has finite index, so this implies that WGH automatically has a finite while group. And it implies also that the class TH normalizer GC makes sense because H is contained in here. And then this class, which expands to the index of H in the normalizer in C, times the transfer from the normalizer in G of this particular connected component times G minus the transfer from H to G, that this is in I infinity of G. C. And if we look at this relation, this is saying that in the case where C has finite index in its normalizer, then all the H's that can occur, their transfers are multiples of the transfer from the normalizer of this connected component once we work modulo I infinity of GC, and this means that A of GC modulo I infinity of GC is a freely reading group of rank 1, and it's generated by the class of the transfer from the normalizer of this connected component, which must contain all of the H's that can occur into G. So then it's a freely reading group of rank 1. Another fact from Lie theory that we have to use now is that in a compact Lie group there's only finitely many conjugacy classes of connected subgroups that have finite index in their normalizers. Here is a reference, and that means that of these things where you get a free group of rank 1 contributed, there's only finitely many. So we conclude that pi 0 G-equivariant of SP infinity modulo torsion is finitely generated. It's of course free because we've divided out the torsion. It's finitely generated, namely by the conjugacy classes of those connected subgroups that have finite while group. Here's a specific example. Let's look at G equals SU2, also known as SP1, the units and the quaternions. This has 3 conjugacy classes of connected subgroups. So the connected subgroups up to conjugacy are the trivial group, then the maximal torus, and SU2 itself. Of these, the trivial group, of course, has an infinite file group, so it will only contribute torsion, whereas this has a finite file group. The maximal torus and the complexity group always has a finite file group, and this, of course, is everything. So we conclude that pi 0 SU2 of SP infinity modulo torsion is isomorphic to Z squared. It's a free abelian group of rank 2, and we know the generators. There's the multiplicative unit 1, and then the other generator is the transfer from the normalizer of the maximal torus all the way up to SU2. This is illustrating again that SP infinity, or this point Z level model HZ I discussed 2 lectures ago, is not an Einberg-MacLane spectrum for the constant global Mackey-functor in general. It is on finite groups, but not on compactly groups in general. I would like to end this lecture and the whole discussion of symmetric product spectra by mentioning a result due to Markus Hausmann that gives information about the higher equivariant homotopy groups of symmetric product spectra for finite symmetric products. As I mentioned earlier, it is of course hopeless to try to calculate the integral higher homotopy groups equivariantly, because after all, already non-equivariantly, this is a hopeless task. On the other hand, if we rationalize, then the non-equivariant story is pretty boring, because the entire symmetric product filtration is constant once we rationalize. But then equivariantly, rationalized, there's actually something interesting happening, and Markus Hausmann gives an essentially complete answer, rationalized and for finite groups. Here's his description. Let G be a finite group. And then the subgroup lattice L of G is the nerve of the poset of subgroups of G. So in other words, this is a simplicial set. So L of G is the simplicial set with k simplices are chains of subgroups H0 contained in H1, and then there's k plus one of them, so Hk is contained in G. This has an action of G. The group G acts first on this poset and then on the nerve by conjugation on the subgroups, and this of course preserves the containment relation, so it induces an action on the simplicial set by automorphisms of simplicial sets. Now we define a filtration. The filtration of L of G, starting with the empty thing, which is L of G is 0, contained in L of G 1, and so on. So this is a filtration by subsimplicial sets. It's given by a chain H0 less than equal H1 less than equal Hk, which is a k simplex of L of G, belongs to the nth filtration, belongs to L of Gn, and is a k simplex in there, if and only if the maximal index is less than or equal to n. If the index of the biggest group relative to the smallest group is less than or equal to n, and then of course all the other indices must also be less than or equal to n. This is clearly preserved under the conjugation action of G, so it is a G-invariant subsimplicial set of the partition lattice. And here's Markus Hausmann's theorem. for every finite group G, and n greater or equal to 1, there's an isomorphism between the graded equivariant homotopy groups of the nth symmetric product, but rationalized. And this is isomorphic to something more algebraic, namely the homology of this nth stage, nth filtration stage in the subgroup lattice with rational coefficients. So that still has an action of G, which came from the action in here. And here you divide out, you take co-invariance in the algebraic sense by the G action. Because G is a finite group and we're over the rationals, you could equivalently put the G orbits in and divide out the G action on the filtration step of the subgroup lattice and then take rational coefficients. Here's a reference for Marcus Hausmann's theorem. Let us do a few consistency checks, reality checks, to see how this result interacts with things that we already know. Two of those checks I invite you to do for yourself. After all, for n equals 1, the symmetric product is just the sphere spectrum, and for n equals infinity, we're restricting to finite groups, it's an unlimited lane spectrum. So please convince yourself that for n equals 1 and n equals infinity, we could have already known this from results that we showed previously. So the new information is really when n is between 2 and strictly less than infinity. I want to do another consistency check and make explicit what this result tells us in topological dimension 0 to see it's compatible with the integral results on the filtration of symmetric products. So let us do this in topological dimension 0. So then we get Q tensor pi 0 G equivariant of SPn by Hausmann's theorem. It's going to be the 0th homology group of the subgroup lattice in filtration n with rational coefficients and then mod G. And as I said earlier, because we're working rationally and we're dividing out the action of a finite group, we can pull these orbits in. So this is the same as the 0th homology of this G space, nth filtration of LG, and then divide it out by the G action and then with rational coefficients. Of course, the 0th homology with rational coefficients of some space is a free Q vector space on the path components of the space on pi 0 of L of G and modulo G. So now we wonder what these path components are, and then you have to recall what the definition was after all of the subgroup lattice. So this was a simplicial set. Simplices, 0 simplices were just subgroups of G and with no condition, and then dividing out the G action by conjugation means we're looking at conjugacy classes of subgroups, but now there's going to be relations coming from 1 simplices and 1 simplices. So this is conjugacy classes of subgroups. Of G. Modulo relations coming from 1 simplices, and 1 simplices were exactly pairs of nested subgroups whose index is at most n. So this is modulo identifying H and K, or the equivalence relation generated by this, whenever K is contained in H and the index of H in K is less than or equal to n. Of course, this is not an equivalence relation yet. You have to pass to the equivalence relation generated by that. And this exactly gives, this is consistent, gives exactly the same answer as when we would get pi 0g SPn isomorphic to the Burnside ring of G modulo In of G, and we take this isomorphism and we tensor it with Q. Now I'd like to go through 2 explicit examples to illustrate concretely how Marcus Hausmann's theorem works. The first example is an old friend, the symmetric group on 3 letters. On the left you see the familiar graph indicating the subgroup structure of sigma 3. This is now also a picture of the subgroup lattice, always considered modulo conjugation. The subgroup lattice in filtration 1 is always a discrete space on the conjugacy classes of subgroups, of which there are 4 in this particular case. The second filtration here consists of 2 contractible components, so H0 of the second filtration has dimension 2 and all higher homology vanishes. Something interesting happens after adding chains of total index 3 and before adding the maximal chains with total index 6. In filtrations 3 through 5, the subgroup lattice is homotopy equivalent to a circle, so there is a non-trivial homology group in dimension 1. In other words, the first sigma 3 equivariant homotopy group of sp3 is rationally non-trivial. Once the filtration reaches the order of the group, in this case 6, we have obtained the full subgroup lattice, which is always contractible. The second example is the cyclic group of order 30. What is relevant here is that 30 is a product of 3 distinct primes. Since this group is abelian, conjugation is trivial and can be ignored. There are 8 subgroups, 1 for each divisor of 30, and the subgroup lattice is a cube. The picture illustrates the relevant filtration of the cube. At filtration stages 15 through 29, the entire boundary of the cube is present, and there is hence a non-trivial rational homotopy group in dimension 2. From filtration 30 onwards, the full subgroup lattice shows up, which is contractible. In much the same way, taking a cyclic group whose order is a product of k distinct primes, the subgroup lattice is a k-dimensional cube. So just before the order of that group, the homotopy type is that of a k-1 sphere. Hence we can have non-trivial, rational, equivariant homotopy in symmetric products in arbitrarily high dimensions. This is the end of my discussion of equivariant and global properties of symmetric products vector, and it's the end of today's lecture, so all that remains is to thank you for your attention.